Session beyond OMNeT. We gathered work that goes beyond the limits of OMNeT, beyond the limits of plain simple framework like INET. Works that, for example, combine various frameworks together. Work that was also for me a new topic, considering OMNeT modeling. At the end, we have a nice talk about something that I've never seen before done with OMNeT. So that's why this session is called Beyond OMNeT. 4 talks and lots of question times and afterwards lunch, so let's have a nice big long session, and we're going to start with Georg and his talk.
Okay, thank you. Hello everyone, my name is Georg Möstl and I'm from the Johannes Kepler University of Linz in Austria, and the topic of my talk today is about the integration of 3 different frameworks so that we get a more holistic approach to simulate wireless sensor networks. So wireless sensor networks, short introduction, it's totally different to what we have seen before. So we have no supercomputers, we have tiny resource limited nodes which are deployed in a geographical region and which shall interact with each other wireless and with their environment. So if we have a look at the basic node, which is depicted here on the top of the slide, we have 4 building blocks. We have a processing unit, typically a microcontroller. Then we have a radio transceiver for the wireless communication. We have some kind of sensor interfaces, for example, if you want to measure the temperature in a geographical region. And the 4th building block are batteries. So the sensor nodes are battery powered and have a standalone operation. So then we organize the single nodes in a kind of network, and we do, for example, temperature measuring in a wood or something like that to, for example, detect wildfires and forest fires. So there are strict, severe constraints imposed to the wireless sensor network. First of all, of course, the energy efficiency. As I said before, the nodes are battery powered and should achieve lifetimes of several years in best case. Then, of course, the timing behavior from the hardware components, but also from the software which is executed on the processing unit of the nodes. For example, if you want to use the wireless sensor network in a closed loop control system, there we have to there we have some deadlines which we shall achieve with the nodes. And of course, the wireless channel, which is not a robust communication media, and this 3 and also the mobility impose severe constraints to the wireless sensor networks. Simulation, of course, has to be shown to be the most cost-efficient way to simulate such networks. Therefore, there are a lot of simulation environments available. This talk is about the integration of 3 frameworks, namely the MiXiM framework, the PAWiS framework, and the MiXiM framework. This is necessary because every framework has a special point of view on the simulation of wireless sensor networks. For example, the MiXiM framework concentrates more on the modeling of the wireless channel and the mobility aspect, whereas the PAWiS framework concentrates more on the energy efficiency and the timing behavior of the hardware, for example, the radio transceiver. And the MiXiM focuses more on the timing behavior of the software, which means the application code which is executed on a node's CPU. So this is a follow-up paper we have already published and made the integration of the PAWiS framework in the MiXiM framework, which was already published. And therefore, this talk and also the paper is focuses more on the integration of the MiXiM framework and the PAWiS framework. So a short background to the PAWiS framework. I think the MiXiM framework is already known. So the PAWiS framework was developed by the Vienna University of Technology. It provides a task-based modeling of arbitrary hardware. And the special point about the PAWiS framework is that it's possible to establish a hierarchy of power consumers and power suppliers which influence each other. And therefore it's possible to create a simple electrical network. The main drawback is that that framework is based on OMNeT version 3, and MiXiM, for the usage of MiXiM, it's mandatory to use OMNeT version 4 and later, and therefore the first step was to port the PAWiS framework to the OMNeT version 4. Here you see the system architecture of the whole system. So highlighted in red are the 3 different frameworks. So here is the SteamSim framework, which, as I said before, concentrates more on the accurate simulation of the application code, which means the timing behavior of the code running on a microcontroller. Then we have the PAWiS framework. On top of the PAWiS framework, the system engineer can develop the hardware models, for example, a radio transceiver model or a microcontroller model. And then we have the MiXiM framework for realistic channel models. Of course, the PAWiS framework and the MiXiM framework are in fact OMNeT simulation models, so therefore everything is built up on the OMNeT simulator. The whole simulation can be compiled to executable simulator, and the annotated application code. Annotation means application code, the functionality, and the timing behavior is compiled in a shared library for each node, and this shared library is linked into the simulator. So the integration between the PAWiS framework and the MiXiM framework was established in 3 steps. First of all, we matched the functionality of the PAWiS framework and the MiXiM framework. The second step was to derive the interfaces and develop the modules. And the third step was to define the NAD architecture, which assembles the node and the network. So here is the functionality mapping for the TX part. On the left side, you have the PAWiS framework. On the right side, you have the MiXiM framework. For example, if the radio module wants to send or transmit a message from the PAWiS framework, this message is first casted to a MAC packet and then handled to the file layer of the MiXiM framework. Therefore, the PAWiS framework is seen as the MAC layer from the point of view of the MiXiM framework. Afterwards, the message is sent to the channel, and of course, self-message is scheduled, which indicates the end of the transmission. And if the end of the transmission is reached, this C message is handled back to the PAWiS framework, and also here is a cast to the air message, which is mandatory because it's needed in the PAWiS framework. The second step was to derive the interfaces and the modules. So here on the left side you have the PAWiS framework, and on the right side you have the MiXiM framework, or to be more precise, the developed modules. So the modules highlighted in gray are mandatory to set up a combined simulation. We have here the MiXiM air client module, which is the type of the radio transceiver model, which has to be used in a combined simulation. Then we have here a new module, or a new class, the PAWiS 5, which corresponds to the physical layer in the MiXiM framework, and the so-called PAWiS decider, which is derived from the MiXiM decider class, which handles the signal processing of the received messages. Between these two, there is OMNeT++ message passing handling used. Therefore, we have here an upper gate and upper control gate. And because this is some kind of inefficient, because OMNeT message handling, you have to create the messages, you have to delete the messages. Therefore, we have a kind of direct connection, which means that the radio transceiver has a reference to the physical layer, and therefore can efficiently handle some kind of control flow. The third part was to derive the NAD structure. In a MiXiM simulation, you have to have a base network interface card module. As you can see here, there are two chain changes necessary to run a combined simulation. First of all, the PAWiS framework needs a kind of node ID, therefore we introduced here a parameter MiXiM node ID. And the second point is that there is a new submodule available in the network interface card, which corresponds to the node, which means the radio transceiver, the battery model, the microcontroller, and the sensor interfaces. And on the top level, which means in the base network component in the MiXiM simulation, we have a logger for serial output of the nodes, and also the mandatory config module, which is needed by the PAWiS framework. Okay, the last part of my talk is about the evaluation. We did some simulation to verify that the integration process was successful. We decided to use a real-life application code scenario, which means we want to measure the received signal strength at different positions in the network. So there is one base station which periodically triggers the sensor nodes, and the sensor node reply with a message which contains the received signal strength. We have here two scenarios. One is a static scenario and one is a mobile scenario. So the static scenario just has a base station on a fixed position, and also several sensor nodes which are arbitrarily deployed in the region of the base station. And the mobile scenario, there we have one fixed base station and one mobile sensor node which moves regarding or corresponding to a mobility pattern and sends back the received signal strength. We compared two models. One is called the gold model, which corresponds to the PAWiS and MiXiM integration, and which was verified by measurements and already published. And we combined we compared the combined simulation framework to this gold model. So first, the static scenario. So you have here on the y-axis you have the received signal strength from the different sensor nodes, and on the y-axis you have the node ID of the node. So here we have 9 nodes, and as you can see here, highlighted in red is that the received signal strength between the gold model and the combined model match exactly. So as a second step, we investigated the energy. So this is the energy of one sensor node. Here we have the energy on the y-axis and several different modules within a node. Yeah, and as you can see here, also highlighted in red is that the energy consumption was determined in the gold model and in the combined model exactly match. Now, this is the mobile scenario. So the base station is located in the upper left corner of the rectangle, and the mobile sensor node moves in an anti-clockwise direction through 20 positions back to the base station, and at every position it transmits the received signal strength of the beacon packet of the base station. And here you see the received signal strength on the y-axis and the position from the mobile sensor node on the x-axis. And as you can see here, there are some positions where the received signal strength deviates from the gold model. This is because MiXiM first introduces a random deviation from the starting position, and the second point is that the MiXiM framework uses a continuous movement, whereas the PAWiS framework only provides a discrete setting of the position. Nevertheless, the absolute error or the absolute mismatch is 1 dBm, which corresponds to the resolution of the radio transceiver model. Yeah, then we also investigated the energy consumption of the mobile sensor node. So here you have the energy on the y-axis and the several other modules available in a node on the x-axis. And as you can see here, the energy consumption is between the two frameworks match exactly. So I come to the conclusion of my talk. The simulation of wireless sensor networks needs a holistic approach, which means mobility patterns, accurate or realistic channel models, accurate simulation of the timing behavior of hardware components and software components, and also of the energy consumption of the nodes. There are a lot of frameworks available, but the frameworks focus on or specialize on special points, special metrics of wireless sensor networks. Therefore, we tried to combine three frameworks, namely the MiXiM framework, the PAWiS framework, and the MiXiM framework. And therefore, we hope to provide a more holistic framework to the community. We did some preliminary evaluation, which gives us some confidence that the system integration was successful. And the most important part is that the framework is available as open source project on the source project. So I'm at the end of my talk, and if you have any questions, I'm lucky to answer them.
Thank you. So we have time for a couple of questions. We have perfectly kept it in time. Questions from the audience? So maybe I'll start. You say this integration of different frameworks. When I worked, for example, with MiXiM and iNet, there was a time when both were tried to be combined. It was always a bit problematic because of the different approaches that both developers from iNet and MiXiM took. They had like different paradigms for modeling things and for handling things. So in this case, you combined three frameworks. It must have been even harder working around those things, like they model this like this, they model this like that. Was there any lessons learned there? Any big things that you can share?
But as a human being, you need some challenge in your life.
I can imagine it was quite a challenge.
No, it's a really good question. So actually, I missed that part.
We have some time.
Yeah. The main problem here, or the main difference, is that the MiXiM framework sticks to the ISO layer. So you have your Mac layer, you have your file layer. The PAWiS framework has a totally different view on a node or a network. They have some kind of hardware-software partitioning. So you have your hardware modules, for example. You have the radio transceiver, your microcontroller, then you have the software running on the node. So from that perspective, it was really challenging to bring the both together. What really helped was that both are OMNeT simulation models. So that helped a lot, and you have all this message passing available in the OMNeT and the gates. The MiXiM simulator builds up on the PAWiS framework. So the hardware models are modeled in the PAWiS framework, and the MiXiM simulator focuses more on the software aspect. So it wasn't that big problem to combine them together. The more complicated thing was to combine the PAWiS and MiXiM framework. But as I said before, because they are founded on the OMNeT framework, it was.
Additional question? Yeah.
Does this mean that the PAWiS framework development has been like resurrected? Because the last release has been quite a few years back with OMNeT 3 point something.
Yeah.
And so you've contributed back the ported version, and they started working again, or?
No, unfortunately, they didn't start working. So I think I'm the only one which is currently working on the PAWiS framework. I did the porting and made a new release within the MiXiM simulator, so to say. But you're right, the PAWiS framework is closed.
How would you see, like, for future work, people look into exchanging the MiXiM part for, let's say, the new physical layer of iNet to bring it to the biggest framework we have right now for OMNeT? If there's some, would it be like big change, quite problematic?
I would say, as a best guess, not that challenging. But typically the problems start if you get into details. Yeah. Yeah, some of the reviewer commented why we haven't used the INET framework because the MiXiM framework was integrated into the INET framework. That was some kind of historical reason, because when we started, this wasn't, the two were distinct frameworks. But you're right, the better way would be to integrate this whole approach with the INET framework so that the development keeps progressing. But from my perspective, I think it's not that big challenge.
So, and maybe last question from me, from the audience afterwards. How much fine-tuning was necessary to achieve like those almost perfect results that you have at the end? Because like I can imagine that the measured RSSE values, if you change like physical modules and everything, they must have been quite different. I mean, when I compared, for example, real measurements to some measurements gained from MiXiM or from even INET afterwards, there were like huge differences.
Yeah.
So
just to make.
I mean, you compare both models.
Yeah, exactly. And that's exactly when the things get more easier. The hard work was the other paper where we compared real measurements with simulation. That was totally horrible. To get the results halfway correct, I would say. This wasn't a big issue because this is just simulation and just two simulation frameworks. If you configure them in the right way, then the two should give the same result. That wasn't that really a big issue.
So the parameters that you have available for physical layers, were they quite comparable, or did they have like complete different parameters, different settings?
We had, we just stick to this freeze-based propagation model, and this can be parameterized in an easy way, just the exponent of the freeze-based propagation. So it would be, I think, it would be more interesting, but also more different if you use a more complex channel model. Then the simulation results, you would have to do more fine-tuning.
One last question, maybe from the audience. If not, he's still around, so we can ask him later on. So, give a big thank you again.